Okay, in this problem, we're going to start with an SUV. We're going to know its mass in kilograms. And we're given that the kinetic energy is 843.5 kilojoules. All right, so from that, determine the velocity of the SUV in terms of miles per hour. Okay, so it specifically asks a certain units there. Okay, so let's get started with the solution for part A. So in part A, we can write down what we know. We know the mass, 2,345 kilograms, and we're given the kinetic energy. Okay, so this is in kilojoules. All right, so what we know, if the kinetic energy is a given amount, we know the formula for kinetic energy is 1/2 mv squared, and we can simply solve for v. Okay, so solving for v, you would get the two coming up, the amount of kinetic energy. Since it's kilojoules, it's times 10 to the third, and then we divide by the mass. So that gives us our answer in 22.82 meters per second. And of course, and then it's just a unit conversion, so I'm going to assume you know how to do that. You can check it. It should turn out to be 60 miles per hour. All right, so that's part A. It's an easy energy problem because you should know the formula for kinetic energy. You can have that on your sheet, by the way, but you need the formula for kinetic energy, and from there you can just plug that in. Okay, next we're going to assume that the engine and the drivetrain have an overall efficiency of 35%. So we're wondering how much chemical energy in the gasoline is required to accelerate from 0 to 60 miles an hour. Okay, and we're going to assume this is on a level surface because it doesn't say that it's not. Okay, and so if it wasn't a level surface, you would have to factor in potential energy as well. All right, so because it's on a level surface, the potential energy doesn't change, and in fact, the only thing that changes is the kinetic energy and the amount of chemical energy produced and the heat that's given off from the engine. All right, so those are things you have to think about. All right, we'll talk more about that on part C. All right, so what we have is we have a certain energy coming in. That's what we'd like to know. All right, and we'll talk about why in a second. All right, and we know the efficiency of this process is 35%. Efficiency of the engine is 35%. So what comes out when we accelerate this up to 60 miles an hour, all right, we're getting that energy from the chemical reaction with the gasoline. Okay, so we know that the energy out has to reach the kinetic energy for the SUV, and it just happens to be that we got that from the previous parts. At 60 miles an hour, the kinetic energy is 843.5 kilojoules. So I write that down. That's the kinetic energy. All right. So it turns out that if you wanted to know the total output in terms of energy, that would be the input energy times the efficiency. Okay, so the rest of the energy would be wasted, okay, in the form of heat in this case. All right, so coming out is wasted energy plus the energy used to get the vehicle moving 60 miles an hour. All right, so we plug in. We know the output energy is 843.5 kilojoules. We divide that by 0.35, and we know that the input energy is 2,410 kilojoules. Okay, so that's how much energy is in the gasoline. All right, so in a way, we probably should have done part C before we did part B. because it lets us think systematically about what's going on in this particular problem. The universal energy equation is that we look at the change in the kinetic energy plus the change in the potential energy, okay, so Ke, Pe, plus delta U. Think of delta U as the chemical energy. This comes from the gasoline. Okay, that's equal to the work in minus the work out. We'll talk about that in a second. Plus heat in minus heat out. And then plus a mass difference, mass in minus mass out. Okay, so in the SUV, there's certain things we're going to either assume to be zero because they are, or we're going to assume to be zero because they're negligible. Okay, so kinetic energy is not zero, but potential energy is. There's no change in potential energy because we're assuming the surface of the road is completely flat. All right, so potential energy change is zero. Okay, and we have to define a system boundary. Let's say it's the SUV. Okay, all right. So the next question would be, what other things can happen? We're not applying any work to the SUV, and we're not getting any work out. All right, the thing's just moving along. How would you apply work in? Well, if you had, another car tailgating behind and pushing it, that would be work in to the system. Or if the SUV was somehow pushing another mass, that would be work out. All right, so we don't have any of that. All right, we do have there's no heat going into the SUV, but because it's burning the gasoline and the engine is not efficient, there is heat coming out. So these quantities are zero. We've already talked about them. Work out is zero. There's no heat coming in, but from the engine there is heat going out. So this term is non-zero. Okay, and then if we think about the mass, what's happening when we burn the gasoline? Is the mass of the gas changing? Yes, it is. All right, through this chemical reaction. Okay, so we know that there is some kind of mass of the vehicle is changing, and it's going out of the car as exhaust. All right, so the car is actually getting lighter. All right, but it's negligible, right? The amount that's changing from going from 0 to 60 is negligible compared to the rest of the system. So we would assume these changes are also zero. Okay, so that leaves us with the change in kinetic energy. We went from 0 to 843.5 kilojoules by burning chemical energy. And so all that chemical energy had to come from the fuel, the delta U. All right, and the wasted energy in this case was the heat coming off of the engine. Okay, so I don't expect that you would be able to handle a really complicated problem like this, but these simple ideas, if I gave you another SUV, I'd want you to be able to think through this and be able to identify the sources of energy for the exam.